Welcome to Spring LIB.
Okay, so we have got an alcohol, and this alcohol was generated, it says, via hydroboration oxidation of some alkene, right? And so recall what hydroboration oxidation does. If we have some alkene, it's going to install an OH and an H, right? But it's going to install them in such a way that we get the non-Markovnikov product. That is, we will get our OH at the more substituted position and our hydrogen at the less substituted position. Sorry, swap that. Our hydrogen at the less substituted position. Dang it, I've drawn the wrong thing. Our hydrogen at the more substituted position and our OH at the less substituted position. And this is contrary to other forms of hydrolysis, for example, with acid or more standard methods, which typically give you the OH on the more substituted position rather than the less substituted position. Now, the other thing that's unique about hydroboration oxidation is that should the carbons that gain the hydroxyl or the H be stereocenters, you will find that in fact they are installed cis to each other. That is, the hydroxyl and the newly installed hydrogen will be cis to each other, which is in fact what we see with the product molecule that we have. So then we can consider what are the different routes to or alkene stock material that could have given this product. So basically any position or carbon neighboring this OH could have been a double bond, and we can consider what the outcomes of those would be kind of in a forward direction. So what I'm going to do is draw the possible alkenes that would give this as a product and see if they do in fact give that product when we step through the logic of hydroboration oxidation. So I'd say there could have been a double bond there. We could have had a double bond there. Or we could have had a double bond here. And what you'll see is that in only one of these alkenes, specifically this one, would be guarantee that the hydroxyl we install at this carbon would be cis to the hydrogen that we install at this carbon, right? Because if we install a hydroxyl here and a hydrogen here, that says nothing about the stereochemistry of a hydrogen there. Likewise, if we install a hydroxyl here and a hydrogen here, again, we have no control over the stereochemistry of this hydrogen. Because we need this hydrogen to be cis to this OH, then we know that the double bond must have been between the carbon with the hydroxyl and the carbon with the cis hydrogen, right? We must have had a double bond here. Otherwise, we would get a racemic mixture of cis and trans products, or likely it would not be actually a racemic mixture because there will be stability differences, but that's beyond the scope of this problem. In either case, this is the only way we know where we can get 100% cis hydroxyl and hydrogen. Therefore, the final answer to this problem would simply be the substrate with a double bond between the carbons with the hydrogen and the oxygen, like so.